Okay.
It's funny, you got that little star right there, man. It's going down.
This stuff is good too.
You got it on your head. You got it on your face, man.
Okay, are there any questions on the homework? I think it's due on Wednesday, right?
Can you do the first one?
Okay. Okay, so the first problem is a first wave propagates in a system of mass springs shown in figure 8.2. I guess I'm going to have to use this later anyway, so I'll see if I can get this up. All right, Bruce.
Kind of bad, yeah.
Surprisingly awkward. So that's what we're talking about, that figure there. Okay, so you have a bunch of masses and hanging out like springs, and then they oscillate up and down and form a wave. Okay. And so the problem continues. It says the masses on the springs are all identical. The masses are 50-gram weights, and the springs all have the same spring constant. The separation of the points P and Q is 0.5 meters, and the wave propagates through the mass spring system with a velocity of 30 meters per second. All right, so let's go back and take a look at this real quick. So P and Q are labeled there. So kind of maybe get some stuff down. So mass. And I'm skipping a lot of intermediate masses. So P and Q at the beginning are at least the and it's 50 grams. Okay.
And the separation 0.5 meters.
And then this between point P and Q, which are the minimum, which seem to be at the same, the same place in the wave, 0.5 meters. All right. So point P and Q, would that be the difference between them be a wavelength?
Oh yeah.
Yep.
All right. So we should say that is lambda.
So can you just do frequency equals C over a wavelength?
All right, and then velocity V was 30 meters per second. What was the relation between wavelength and frequency?
Frequency times wavelength equals speed.
Yeah, so frequency times wavelength is equal to V. So if I want to know the frequency, that's just the velocity divided by the wavelength. Okay, V, suppose that the oscillator at point P has an amplitude of 25 centimeters. What is the spring constant of this oscillation? All right. So how are we going to do that one? So amplitude.
You need to get omega and then.
Yeah, well, let's see if we can get omega. I don't think that amplitude has anything to do with the spring constant.
No,
You
that's
just
why.
do
Right?
spring force is KD.
Yeah, you could. We could figure out what the spring force is.
Doesn't it?
But then what is the distance? Stress.
You remember each one of these is a simple harmonic oscillator, right? So with this frequency being this, that's also the frequency of the oscillator. Is that clear? As the wave goes through?
So will time matter in this?
Well, it will, but if you have a wave that's just constantly going through here, each of these is just going up and down.
The
When it's
oscillation there.
oscillating at the same frequency as the wave is going across, right? Because as this thing goes up and down, that's like the equivalent of having one wavelength go through, go past it. And so if that's the case, then wave omega, we know omega for a simple harmonic oscillator, right?
Yeah.
It's square root of k over m, and that's 2 pi times the frequency. So we know what m is, we know what the frequency is now from here.
Mhm.
Go back and solve for k. So k is m omega squared, yeah. And then put it into omega. Okay, and then C, and suppose that we have the amplitude. See, that's very strange why it's talking about. Anyway, with each of the masses is oscillating, how does the velocity of propagation of the wave change? Well, it shouldn't, should it? Yeah, see, if I change the amplitude for a simple harmonic oscillator, right? It doesn't, well, actually it might. No, it doesn't. So if I change the amplitude, I get the same period, don't I, for a mass on the spring? That's one of the characteristics of simple harmonic motion, is that the period of oscillation is independent of the amplitude. And so if that's the case, I have the same frequency is the same, right? This, does the wavelength change? Yeah, the wavelength I don't think has anything to do with amplitude, right? So what we're left with is that the frequency stays the same, the wavelength, there's no clear reason, it doesn't appear to change. And so that means that the velocity would remain the same. And suppose that we double the spring constant in each oscillator of the system. How would this change the velocity of propagation? Now, would that make it change? Yes. If I double the spring constant, that changes by 2. So omega gets multiplied by a factor of the square root of 2. And then that means that the frequency would change by square root of 2. And then that means that velocity would change by square root of 2. Okay. That makes sense?
So that was for part D, right?
That was for part D. And then part E, given the number of oscillators shown in figure 8.2, what is the phase shift between 2 adjacent oscillators? All right, so what does that mean? That means, what's the, if I treat, okay. So if I treat this as a wave and plot maybe the y position as a function of distance, maybe the y position is up here and it goes down, and so after one wavelength it comes back up. The phase difference between here and here is basically the angle in radians for an equivalent circle that's rotating. If this is the y position on a circle, that's rotating. If I look at a little point here and then look at the y position of it, up here, as it goes one full turn around, it changes by 2 pi radians. We can treat the angle with respect to its initial position as what we call the phase. So this is kind of confusing. So think of this as a sine wave, okay? Sine wave is going to go like this, right? Or cosine. What's the angle of the cosine at these various points? So here would be 0. Is the phase is 0. Here, phase is 90 degrees, or pi over 2. Here the phase is minus pi. Here the phase is 3 pi over 2. Here the phase is 2 pi. Okay? So if I kind of think of this as an oscillator, the phase difference between this and this thing, if this is at a minimum, this is at a maximum, or this is, this would be pi over 2 difference, because if this was at, so this is one wavelength, isn't it? So this would be a pi difference if I had just 2 oscillators here, right? So if this is at a maximum distance, this would be at a minimum distance. This would be like looking at these 2 different points. So maximum y, minimum y. In between here and here. Now, they have instead, how many oscillators are there between P and Q? I think there's 8. There's 8 oscillators between P and Q.
So it might just be.
So if I divide up one wavelength into 8, this is 0 is the first one, 2 pi is the last one. If I divide that up into 8, each one's pi over 4, right? Pi over 4, 2 pi over equals the phase difference between adjacent oscillators. Take 2 pi is the phase difference in one wavelength. There are 8 of those oscillators in every wavelength. So the difference in phase between the different wavelengths, between the adjacent ones, would be 2 pi over 8. Does that make any sense to you guys?
Yeah. Well, it asks for the whole. Is it asking for between for the whole image, or just between P and Q? Because the whole image would be like twice.
I think it's asking, what did it say, between the adjacent oscillators?
Between they should increase between 2 adjacent oscillators.
Yes, that means between the 2 neighboring ones.
Yeah. So it'd be okay. 1/8
So that'd be
or 1.
Yeah.
Yeah. Pi over 8.
1/8 of the 2 pi.
Sure. Okay.
The total.
That makes sense.
So when you counted the oscillators, you counted, like, was B counted in there?
All right, let me see this. So here's P. 1, 2, 3, 4, 5, 6, 7, 8. So 8 spacings. Yeah. So 360 divided by 8 would be the angle difference in the degrees. If I plot it as in degrees and in radians, it would be pi over 4. Do they ask in degrees? I'd be fairly surprised if they did. Oh, they do. All right, so if it's pi over 4 radians, how many degrees is that?
It's pi over 4.
What's pi over
Pi
4
over 8.
radians
In degrees?
in degrees?
90.
So that'd be 1/8 of total degrees in a circle. How many is that? It's 45, right?
But it is 2 pi over 8, right? Radians. Pi over 8.
Pi over 4. Because it's 2 pi over 8. Just 2 pi radians in this total thing. And
Divided by
between 2
8.
oscillators, there's
Oh.
equal spacings.
Okay.
Or
2
360
pi
divided
over
by 8
8.
is.
So that'd be 4 pi. Okay.
Okay.
Pile book, yeah.
All right, and F, if this phase shift is halved, what is the velocity of propagation in the wave? All right, so what does that mean about the wavelength? If I go from pi over 4 or 45 degrees between adjacent oscillators to pi over 8, did I lengthen or shorten the wavelength? So here I have fewer, here I have a much shorter wavelength, right? I only have, the wavelength is 2 spacings between oscillators. Right? There, I had an 8 spacings between the oscillators. And that made the 2 pi over 8 be the phase shift between the angle between 2 nearby oscillators. If I had 16 here, which would be having the phase difference, how many oscillators are in the full wavelength? 16, right? Well, if the oscillators are all the same, they don't change, then I basically doubled my wavelength, didn't I? If I double my wavelength, what did I do to the velocity?
Times 2.
Double it to this.
Wait.
Good. If, provided I keep the frequency the same. Yep.
Wait, what's the phase shift?
Phase shift is the angle. So if I consider one wave as having 2 pi radians or 360 degrees, one wavelength as having that, then the phase is the difference in angle between one point and the point that I'm interested
So
in different
45.
phase with.
But we just solved for, right?
Yeah, so it'd be 45 for the original case.
Okay. And
Now
now
we
we're
have that, so we want to make it 22.5.
because are we adding another one between each one?
No, we're not adding another one, we're just changing the wavelength. So the oscillators look the same. It's just that
So we're just squishing it this way.
you're just spreading it out because
Oh.
it takes more oscillators to do one wavelength. Yeah. So that's a good one to think about. This is definitely something that's tricky to get your head around. All right. Well, we were doing superposition and interference of waves, right? And I started out last time with the demonstration of, or I ended up last time doing a demonstration of this, but it wasn't set up that easily to see what was going on. So I'd kind of like to go through that a little bit more today, and then also look up. Hopefully, we might understand something called, understand some of our radio receivers just a little bit better. What's going on? Okay, so we mentioned at the end of the day that if you have a string that has a wave traveling along it, and one end is fixed, as this wave travels and gets to the fixed end, the wave actually flips over when it gets to the fixed end. It reflects opposite side of the string. This isn't a great drawing. I'm going to draw one pulse and see what happens. So if I have one pulse along here, and it gets to the end. Say I took a string and just flipped it up like that, went back down. this pulse would be traveling along here with a speed v. When this got to the end over here, it would reflect back, but it would reflect back opposite direction. Upside down, on the other side of this string. Okay. Does that make sense? All right. What I have here is something that's constantly putting little pulses in the string, in the string in a harmonic way. So let's see if we can see what happens. I'm going to draw a very simple case where between the two endpoints of this string, I have 1/2 of a wavelength. So this is half a wavelength here, right? Let's just say this is traveling like so. And if I were to continue this, the spring by this thing that makes the string move, it would look something like this, right? I'll do one full wavelength. So if this shifts forward a little bit, so this whole wave like this is all moving in this direction with whatever speed the wave had. So I'm going to try and draw this shifted over a little bit. So a little bit later, you would have this basically look the same, but shifted over. A little amount here.
The other side of your.
But when this one got to the end here, it actually turned around and reflected back. So, actually, this would be forward, shouldn't it? Very good. That makes a whole lot of difference to what I was doing. Okay, so this whole thing is moving forward. And when this wave got to the wall here and was fixed, what it wanted to do was to reflect upside down and backwards, right? So there's another wave that's kind of coming out that looks something like this, okay? So this is a little confusing. As this wave travels, when it hits the wall, it's on the opposite side of where it was, going the opposite direction. So the reflected wave would be looking like something like this. Okay. Now it looks like these two would have. It's confusing because these don't start at the same point, right?
Fix or have to start at the same.
Yeah, this would be. Yeah.
So if there's like a horizontal middle point, it would just
Yeah.
be like reciprocated over the middle point.
Yes. Yes, that's right. So if I started at a middle point and have a fixed number of wavelengths in here, this wave is the distance from the middle point that it's moved from. That's what these things are indicating. So if it's
Well, like
above the
when
middle point,
When it hits the wall, it'll just be underneath the middle point, the same distance.
yeah, that's right. That's right. So that's the key
Why
point.
did it go up instead of down? Shouldn't it doesn't do down?
Which one?
Like if that one, the yellow one you're pointing at, the one reflecting, shouldn't it go down here and go down?
Yeah, that's what it did here. So it's going more towards its middle point here, right? So the reflected wave would be going more towards the middle point, but from the opposite side. Okay. Anyway, this is where, hopefully this will make some sense and you'll see it. Let's say I have a spring, or a string, with 1/2 of a wavelength here. If this weren't fixed, if the wall weren't fixed, the rest of the wavelength would look like that, right? But when it hits this wall, it's reflected opposite the way it would be. So it's reflected up like this. So this wave's traveling this way, and this wave is traveling this way. Okay. If it just so happens that there's 1/2 of a wavelength between these ends, so this distance here between the ends of the waves that are lambda over 2. Then when this wave gets to the end here, it's reflected back. And then when this wave gets to the end here, the red one gets to the end here, it gets reflected. The yellow one gets to the end here, it gets reflected back, up again. And these reflected waves going in this direction and the waves going in this direction, they're all what we call in phase, and they add up together. And what you get is you get a maximum possible wave size. You get something called a standing wave. And that's an example of that is right here. So if you guys...
Yes, so
Okay. This is what I have.
Interesting, but the sliding on this, when we did this the other day, you guys saw the string going over. Where I was standing at the end,
Yeah.
it was looking back.
Really?
Okay. Now can you guys come over? Why don't you stand up and just come by and see this, okay, real quick. And, hopefully, and then what we'll do is turn off the lights.
Yes. You guys see this? How it's up? So what I have here is I have the constructive interference between one wave traveling this way and one wave reflected back. So how many wavelengths are in here? Actually, there's one, because each one of these corresponds to 1/2 of a wavelength. Oh,
All right. One of these corresponds. So if I were going to draw the wave coming from the string, the string vibrator, it looks, yeah, it looks something like this. So this is distance. Here. And if I were to draw the wave that's reflected back, it looks something like this. And then these waves are going up and down. These waves are, when they're out of phase, they look like this. And so you get waves going up and down like this. And then this point here never really moves. You see that point? That's this point here. This is called a node. And these points where you have the maximum vibration of the string, this is actually twice the amplitude of vibration here. These are called antinodes.
Oh, you're gonna do that thing?
Yeah, let's go ahead and see this, by the way. You want to hit the lights over there? Actually, probably with the main room light. Let's see if we can do this. It takes a little bit to warm up. Look at that. Now look, can you guys see this? I can make that thing look like it's stopped, can't I?
Mm-hmm.
And I can move it around. Change directions if I want. So what's and we'll look at this in just a second and see what this is. You guys see this? Does everyone see that? Yeah. It's pretty neat, isn't it? You can see the node, it's not really moving. Yeah. Just it. Yeah. Let's go ahead and see what's going on here. This is sort of related to superposition of waves, and but more importantly, it'll be related to very closely related to what we call like FM radio. You see that? It sort of stopped for some reason. I think when it does that, it kind of skips it. It skips a flash. So if I can slow it down exactly and look at this, I can tell what the. I think this is when it's jump. I can also make it slow down at this speed too. This one looks a little slower, doesn't it? All right. Well, anyone want to play around with this at all, or are you good? I don't know. This is pretty cool. We'll see if we can figure out what's going on. Okay, so real quick, if you want to get that standing wave set up, you have to have the length of the string be either half of a wavelength, so that the reflected and the incoming waves are in phase, or you can have it one wavelength, or two or three halves of a wavelength, or anything like that. But you need to have it, length of the string needs to be some n lambda over 2, where this is half of a wavelength, this is an integer. So it has to be an integer number of half wavelengths. So 1 half wavelength, 2 half wavelengths, which is a wavelength.
What is that for, the condition for?
This is the condition to get a standing wave like what you saw with the nodes and antinodes, where you get the constructive interference at a given point between the reflected and incoming waves.
Like this, how did you know how far apart to make it?
Just kind of move it until you
Oh,
can
until you can, I see.
Yeah. So, There is, you could figure it out. Turns out that this thing goes back and forth at the same frequency as AC power. And what's that? That's like 60 hertz, right?
Yeah.
So frequency would be 60 hertz. And there's a formula for the wave speed in a string. We don't have to really know this at this point, but it's the square root of the tension over the mass per length of this string. So L M. So this is mass of string. Length of string. Tension.
In kilograms?
Yeah, well, if you have tension in newtons,
Oh, yeah.
you should have this mass in kilograms. Okay? This will be kilograms, meters per second squared. Divided by kilograms, multiplied by an L, that's meters squared per second squared. Take square root, that gives you your, that has at least units of velocity, and it turns out to be that. So in principle, I could, if I knew all these things, and I knew the frequency, I could get the wavelength, and I would know how long exactly I want to make this string. Right? You have an integer number of half wavelengths.
But this is the same as electricity. With your phases, like you have 2-phase and 3-phase electricity. Is that like
That's
on
related.
3-phase? You've just got another wave in there. Is that?
That's right.
What that is?
So what you're talking about is actually really interesting. If you were to look in your house, there are two different voltages you can have in your house, right? So you can have 120 volt, you can have 240. Probably your dryer, and if you have an electric stove, those work off the 240, and that's more or less about it. The way that it's working is you have, if I were to look at voltage as a function of time, and I'm sorry I'm going a little long, you have 3 wires going into your house. One wire has a voltage as a function of time, looking like this. One wire is a grounding wire, so it looks like this. And then another wire is exactly opposite the first wire, and it looks like it has a voltage like that. What gets applied, we're looking at differences between two of these. So if I'm looking at, if I call this 1 and 2 and 3, the difference between 1 and 2 it looks something like this. If I were to look at the difference between V1 and V3, it starts out as 0 here, right? But over here it's going to be twice as far. It'll go up to twice the distance. Go back to 0, twice the distance. Go up to 0 like that. And so this is the 120 volts. This would be the 240 volt one. So it depends on where you put your, what wires you hook into, what 2 wires you hook into, is where your big or small voltage will come from.
Yeah, for your 110, you only plug one of your wires in. For the 220, you plug both your hot wires in.
Yeah.
Or you're actually running off of 2
Both
hot
of them,
wires.
yeah. Yep.
Now, what's with the phase? How does that work?
Well, these 2 hot wires are out of phase by 180 degrees.
Now, how does the 3-phase, how do they shove that third one in there?
this is 90-degree difference from this one, right? So, or this one's just 0, I guess. So I don't know. I don't know. This is about as much as I know.
Fair enough.
Okay, there's a difference. Yeah, there's a difference between the peaks and the actual voltage. What you have, your average voltage is the RMS voltage. So the peak will be different. Anyway, we'll leave that be. This is something that you get into in physics too.
Will it be complicated?
Finish this up. Okay. Oh, FM radio. Yeah, we're trying to figure out how this thing works, right? Okay. So let's go ahead and imagine that we have a y position or a position of this string at any given point in space. And we look at it as a function of time. Okay, what's this little chunk of string doing as I'm vibrating it? Just going back and forth, right? And so if I looked at it and plotted this as a function of time, it would look like this. And the difference between these peaks would be the period of the motion. That'd be 1 over the frequency. Okay? The time between those two peaks. All right. Now, if I have a strobe light going on, what I'm doing is I'm shining the light at a certain frequency, a sharp burst of light at a certain frequency. So the light turns on really quickly and then turns off, turns on, turns off, turns on, turns off. And what it does when it turns on is I see the string where it turns on. So for instance, if I were to turn it on and see a bright spot here maybe, and if it was at exactly the same frequency as the string was moving, in, the light would turn on again right here, and the light would turn on again right here, and the light would turn on again right here. And those would be the only times I'd see the light turn on. And so what would it look like the string was doing?
Straight.
It would just be a straight, it would look very straight, but it would be not at y equals 0, it'd be like straight out at a little distance away from that. And it would not be moving. Okay? If I didn't have the frequency quite adjusted, so that I turned it on a little bit off from one period of the string, maybe a little bit shorter, I would start to see this, wouldn't I? And what you would see is that the string would be moving, but quite a lot slower than it actually is moving, isn't it? And in fact, how much slower depends on the difference between the period of the strobe light and the vibration and the period of the string, right? If it's right on, then this would be right on, and the string would look like it would not moving at all. If I had it a little bit off, you get something like this, so that you would get a slow periodic shift in where the string's position is. But you would see that if I kept